Hello and welcome to today's IWCS webinar. My name is Connie and I'll be your Cisco WebEx producer for today's event. Now I am pleased to turn the webinar over to Ed Fenton, your IWCS moderator. Ed, please go ahead.
Thank you, Connie. Our IWCS webinar series event is hosted by the International Cable and Connectivity Symposium. I am Ed Fenton, a cable industry advisor working with the IWCS team. As Connie said, if you have any questions, please use the Q&A box on the bottom right of your screen to post a question anonymously. If you wish to contact the presenter or IWCS after the presentation, you will be given the contact points at the end of the webinar. Please note that IWCS does not distribute the presentation slides from either our conference sessions or these webinars. However, please feel free to contact the presenter directly and they will respond individually to you. Today we welcome Ken Cornelison, industry consultant, Hitachi Cable America in New Hampshire, USA, who will be presenting his paper on performance comparison of reduced diameter Category 6A cables. Ken Cornelison is an industry consultant with experience in the design, development, and testing of a wide range of copper and fiber optic cables and processes. He was graduated from Rose-Hulman Institute of Technology with a BSEE in electrical engineering and from Ball State University with an MBA. He has also worked with cable high-frequency testing and monitoring equipment and develops new equipment useful for twisted pair cabling process control. His most recent experience is in the design and development of new category cables with enhanced performance. Ken, we welcome you to present at today's IWCS webinar series event.
Well, thank you very much for the introduction. I'm pleased to be here today to present the paper that we did at IWCS on the webinar, and I welcome everybody who has joined in to listen to this presentation. So again, thank you all for being here. I want to start by, again, the title of the paper is the Performance Comparison Reduced Diameter Cables, because a lot of things happen when you try to bring the diameters down and maintain performance in other categories, other areas. So alien crosstalk is really a key addition that's been in the industry standards for performance requirements, of course, and that's so well known, and a lot of testing is done, is reasonably well understood in wide areas. But of course, the challenge over the years has been to try to bring the overall diameter of those Category 6A cables down. So there's been a lot of work in different kind of techniques to do so. And because the UTP cables need to be larger than the alien crosstalk, then you want the smaller cables, of course. And to do that, there's been specialized barrier layers to introduce to the cable, which actually enhances and alters the magnetic field around the pairs. And they do indeed improve alien crosstalk and result in smaller cable diameters. But the point of the paper today is to investigate what else is going on in different scenarios that may be happening in addition to the reduction in alien crosstalk that's being observed. So we want to compare the performance of different category cables across different types of noise immunity. So electrical interference, particularly from outside events, is growing importance. We're going to talk about that a little bit. The summary of cables that were tested, we'll touch on those so you understand what the cable testing was done, how the cable testing was done and what with. And then we'll be talking about electrical test results, including pair balance, which we see as a critical parameter, alien crosstalk performance as well. Coupling attenuation also is very interesting to view and compare against pair balance. On the EMC side, we have data with 10 gigabit Ethernet, HDBaseT link, and also we feel rather important is the induced pair voltages on the pairs when they are subjected to outside influences. We'll be talking about, of course, coupling mechanisms in the different cables, and then, of course, conclusions. So alien crosstalk effects are well known. There's standard testing out there, and for the 6-round 1 cable, that's very well known. But alien crosstalk has a specific type of coupling, cable to cable. And we feel that there are probably different coupling mechanisms based on different environments, so we wanted to explore those and understand better what's happening in different environments. So obviously, this outside interference besides alien crosstalk is driven by the fact that more of the Shannon capacity, or essentially the noise floor of the cable, is being used. So all these new applications out there require lower noise in the channels, stronger signals, and better signal-noise ratio. So the 2.5 and 5 gigabit protocols recently out for state issue. There's also things like single pair developments happening that will be looking at even stressing the noise floor and the noise envelope even harder. So it's worthwhile looking at these things. HDBaseT is another development, continuing to grow the data rate and needed by the high definition 4K and high frame rate, et cetera. So there are trade-offs in the barrier layers that are out there, and of course you have the suppressing the differential mode, coupling cable to cable, but they also, you have to watch out and understand how the common mode coupling is behaving as well. And so this testing was really focusing on both common and differential mode coupling of the cables to the outside environment. The cables tested were all 4-pair cables. They were either a UTP construction with no electrical barrier over the 4 pairs, or they were a 4-pair construction with a similar core, but also a barrier layer over the outside. And we characterize those by the design letters. We follow that through the paper. This is a test result of the balance of the cables that we tested. And there is some difference, but what we find actually, we feel there's more similarity than differences among the cables. We also did a study, it's not in the paper, we did a study on the noise floor, the balance measurements, and what we find is that this is believed to be a true representation of what the cable actually is and not a limitation of the balance or the test mechanism itself. So we do see that we believe the cables truly are more similar than different in balance. When we get to alien crosstalk, we find dramatic differences, of course, that are not related to the balance. And we find that design view, which is a typical UTP type cable, has, I would say, kind of the expected curve seen for years in the industry since 6A came out, where you follow the requirement line and the several dB margin to the requirement line. But then what we see is for the other 3 designs, which is the screen cable and capsulated kind of cable and some with a discontinuous type barrier, we see distinct differences. So that was of interest. They all meet 568 requirements, but they have different characteristics in their performance that I think need to get some deeper understanding of why these differences occur. So, as I said, the UTP follows the requirement line. Design D has some more significant spikes and structure to the response curve, and E and F are essentially uniformly low and uniform in alien crosstalk response. The coupling attenuation test was done with an industry standard technique using an absorbing clamp mechanism. We use absorbing clamps so we can test UTP-type cables and not require shield or screen connections, of course. And all the testing was done at the same laboratory. I'm using the same equipment, so all cables have the same, essentially, baseline testing. And what we found there was interesting because it's known or understood that balance is a key contributor or strong related to coupling attenuation, particularly for UTP cables. But what we found is that coupling attenuation actually does change with the overall design and is affected by the barrier. So what we see is that the design F and the design E have pretty good, or it's just a pretty good, to say lower, better coupling attenuation. And then design D is interesting because it has lower coupling attenuation than the other pairs. So we wanted to, again, investigate that a little bit further. And these differences were not seen in the balance measurements taken on the same cables. So again, we have the differences between the coupling attenuation, and also what's interesting, it tended to follow the alien crosstalk results as far as the way the curves look shaped compared to the balance curves. So we saw some correlation between the alien crosstalk and coupling attenuation. In the EMC chamber, we generated RF energy using a log periodic antenna in an anechoic chamber. And you see the arrangement of the cable that was done on the dielectric frame. So we had about 30 meters or so of cable under test in this chamber, and the remainder was outside the chamber. We used a frequency range of 80 to about 680 megahertz depth of frequency. That frequency range was particularly chosen because the power spectral density, PSD, of the energy that Ethernet was in that range. We used unmodulated CW continuous wave, and we went to a frequency held, and we used 61 frequencies with 10 megahertz steps at each sweep that we did. We also used field strengths of 1, 3, and 10 voltmeter, which matched the guidelines and the MICE requirements. Test frame was chosen to match the uniform field strength window according to IEC standards and the calibration plane in the RF chamber. Again, the 30 meters was quite calibration in this plane in the chamber to induce voltages on the cable. They were patchless plugs to bit array test sets. So the quick test equipment used was either an HDBaseT test unit, a handheld quantum data unit that was used to understand the data transmission. And we also used a 10 gigabit PHY, physical interface device PHY, and monitored the packets and packet loss through the indicators on the physical device itself. So with those devices, we were able to monitor the feedback. And this is an example of, on the right, you see we have no errors in the packet, and we have good data throughput. And then when the signal is too strong, we actually can have a link loss where it has to auto-negotiate and return to operation. And that situation is seen on the left there, where all the indicators are red. And then the upper indicator light on the left there was indicated whether we had a packet loss or a link loss. So just to understand how we got to the point of understanding data for whether we had link losses, which is more severe than just a packet loss. So just an example that we see that the frequency, the response is more sensitive up to about 400 or so megahertz. And when you look at the density of the actual 10 gigabit signal, the power spectral density, you would expect the effect to be fading off at the 400 to 500 megahertz range because there's just not that much energy out that high in a 10 gigabit Ethernet link. So this kind of style of response where you see a lot of events at the low frequency and not any at the high frequency is reasonably expected. So what we did, we actually counted the occurrences when they occurred at frequency changes and tabulated for each frequency step. We monitored how many of those frequency steps resulted in either a packet loss or a link loss. So what we saw with design D, that 1 volt per meter had a few packet losses, which was not too severe, and the other cables actually had no packet losses or link loss events at 1 volt per meter in our RFI chamber. Again, 1 volt per meter is called a mice 1 or an E1 environment, and typical in office environments, et cetera. However, when we bring the voltage to 3 volts per meter, we see a much greater difference among the cables. And what we see is design F, which is a screening cable, performance at best, which would be expected. And then design E, B, and U, again, have many more load packets as well as link losses. So, for instance, talking about design U data, on 22 of the 61 steps, we observed an actual packet loss, which is a short-term disruption in the data flow. And actually, on 10 of those steps, the link actually had to drop and had to auto-negotiate. So that's the difference between the blue and the orange, is whether we had a short-term, just a few packets jumbled, or we actually lost the link itself. And of course, the link loss is much more severe on the end. At 10 volts per meter, we saw that the cable were essentially overloaded. Even UTP cable was essentially, there were 37 events there, but they were both packet and link loss. And however, screen cable was essentially not affected by even the 10 volts per meter. So this builds just a reminder again that the screen cable is much better in this, but that is expected, of course, in the design of the cable. Now, for HDBaseT testing, what we did was connect those cables in that same environment to the quantum data unit and monitored and measured and recorded the data at the 2160/30 hertz refresh rate. And we looked at the bit error rate reported based upon the output of the unit. What's interesting is the design B was not put in the chart, because what happened with design B at the 3 volts per meter, we saw substantial errors. Sometimes no signal error occurred. It just was not really feasible or meaningful to gather the data. But the other cable designs had essentially very low data errors at 3 volts per meter. And design U, the UTP cable, did have kind of a resonance or a sensitivity around 250 megahertz. However, when you zoom in to the data a little bit and look a little closer, this is the same data but at a much more compressed scale by a factor of 1,000. We see that there is differences among the cables, and we see the design F, the screen cable, had the lowest number of errors. Design E did have some errors, but also had sections of the frequency spectrum that were very low. And design U, the UTP cable, also had areas of low errors, but not quite as low as the other two designs. And these pair voltages, we expect those to have some correlation with the bit error rates and the link disruptions, of course. We believe actually that the measurements of pair voltages can be more deterministic and repeatable compared to bit error rate testing. A point on that is we believe, well, actually a scene I should say, is that the fives or the network cards don't like to be surprised. They actually react much more strongly to changes in the signal compared to steady state signals. So things that happen that are more random in nature or more important actually are more affected on the unit card. So we measured differential and common mode voltages as we subjected the cables to the interference, and we measured the voltages on both shortest and longest leg pairs in the cable. I will make a comment that we found very little difference in the data between the two leg lengths of the cable. The voltages seem to be most affected by the design of the cable and, of course, the voltage level in the chamber. So what we see here is the differential mode voltage captured at 3 volts per meter in the EMC chamber. And you see the ranking of the stepping of the data. Design F had the lowest overall voltage of the screening cable. Design E was in a similar range. Design U was, of course, a little bit higher. And then to match the correlation to the coupling attenuation and the other data we saw, the Design D had the highest coupling. So again, interesting results, and they actually correlate more closely to the coupling attenuation than, say, pair balance and the other measurements. And the common mode voltages, basically is a measure of the voltage on each separate conductor. Twofold is one you'll see, if you compare on the other chart, of course, the signal is much stronger, of course, because you don't have the cancellation caused by the balance. But we see the overall ranking, and this overall ranking also tends to agree with the trend we saw in coupling attenuation. What we also did was look at the difference between the common and differential mode, essentially an evaluation, what we're calling effective or apparent pair balance. So what we see is the pair balance was quite similar among the designs, which also correlates to the observation we saw where the actual measured balance in the laboratory was very similar from cable to cable as well. So this result is consistent with the overall pair balance. But again, pair balance and coupling attenuation and coupled voltages are the ones that tend to correlate, but not with pair balance. So what we're seeing is that the common mode and differential mode coupling, we believe, have coupling mechanisms that are much different between each other and among cable designs. When you look at EMC and coupling attenuation measurements, what the testing is about there is generating a common mode signal and looking at the differential mode in the pair. And also, of course, you're getting common mode coupling in the pair as well. So you have a much more direct one mode to the other mode coupling going on in the EMC or a coupling attenuation test. When you look at UTP alien crosstalk testing, what you have is common mode and differential mode energy in the cable, and you've got separation between the two cables providing some isolation. And then those common and differential mode energies transverse the space between the cables and, of course, then generate CM and DN, common mode, differential mode in the other cable. Of course, the cable spacing is key in this equation because then if the bigger the cable, the larger the spacing and the lower the coupling, which led to big the cable diameters. Coupling is different between SUPP type cables and those cables with the barrier. So here you've got differential mode in the pair, of course, coupling to some kind of common mode in the shielded barrier. You got cable spacing again, but cable spacing tends to be less critical because a lot of the coupling between the common mode coupling gets handled in the conversion to the shielded barrier. And then, of course, back again from the shield into the pair. So we have different coupling mechanisms depending on the situation and the environment. And it's these different mechanisms that are important to understand and characterize and measure so we can better understand how cables will perform in different environments. So we did find that alien crosstalk and pair balance are not good predictors of EMC performance. It is possible to have what you might say so-so alien crosstalk performance and still have good resistance, good EMC performance. It's also very possible to have reasonably good alien performance and maybe not quite as strong EMC performance you would like to have. So in conclusion, parameters with lack of correlation to noise immunity include the pair balance. And of course, alien crosstalk, we don't see a strong correlation there. And we see the parameters with correlation to noise immunity are coupling attenuation, which seems to have some predictive capability. And also what's important is we see that the induced pair voltages, we seem to see those that are correlated with both coupling attenuation and the bit error rate performance. So when we look at the EMC performance based on the data we've gathered for this paper, we would look at things like coupling attenuation as a measure, and of course, induced pair voltages. I will say again that the bit error rate testing is valuable, it's important, and it provides some perspective. But once again, there's been consistent observation that the PHYs don't like to be surprised. And when you have a change in frequency or a change in interference, you tend to see more disruption of the link than when the interference is steady state. So, for instance, in maybe a local radio station is transmitting a very consistent radio wave, the PHYs tend to adjust to that and essentially cancel that out, and they have a lot of DSP, digital signal processing, to do so. When you have a random occurrence, say maybe a motor turning on and off, a fluorescent light generating ash in the environment, that's more random in nature, and the PHYs don't seem to be able to react to that as quickly, so it generally leads to additional packet or link losses in those types of situations. So that is why we believe that induced pair voltages are a key measure of EMC performance, in addition, of course, to bit error rate, which gives you some perspective and context for the values of pair voltages. So the design effects we saw here, of course, is that 6A cables with a well-designed barrier can indeed have both alien and noise immunity. It can be better than a UTP cable with a smaller, and also gain smaller diameter in its design. 6A UTP cables do offer an acceptable level of immunity for many applications. For instance, the data in the E1 or the MICE-1 table we showed earlier, again, we saw essentially no packet or errors. But when the noise gets a little worse, or you're worried about something maybe close to the cable, then those differences in cables do tend to be much more pronounced. So barriers are a good thing for keeping small diameter and alien crosstalk happening at the same time. They should be, however, carefully designed to optimize performance in different environments. And of course, screen cables do offer, indeed, the most robust level of noise immunity. So thank you very much for listening to the presentation. Looking forward to questions as I can hopefully answer. Thank you.
Ken, thank you very much for presenting this important topic today. We'll take as many questions as time permits, starting with this first question. Is alien crosstalk the same as cable-to-cable crosstalk, or are we more concerned about outside interference EMC?
We are concerned about both. Both cause noise, and in the 10 gigabit and higher data rates, you're just worried about any kind of noise. And so the point of the paper was to understand that there is ANEX, there is noise induced by alien crosstalk, but there's also different kinds of noise that do generate from outside the cable that can actually have a more severe effect than cable-to-cable noise.
Okay, thank you. Next question. What are the data security issues, if any, for reduced diameter Cat6A cables? Are other cable design measures taken to mitigate outside eavesdropping?
Interesting question, but I don't have a good answer to that. I will say this, is that when you look at eavesdropping, you're looking for, the typical eavesdropper would try to find a way to couple energy from the pairs, from the cable, into some outside device. So you would expect, a general trend that UTP cables be the most susceptible to such a thing, because we know through alien crosstalk testing that energy radiates outside the jacket. And fully screened cables would be among the more resistant because the outside energy is controlled and contained within the core of the cable. So I would expect some cables designed to have varying sensitivity to eavesdropping, but I don't have any real data to describe that any more in detail, though.
Okay, thank you. Next question. What is the impact of using physical or more rigid separators, such as crosswebs or jacket configurations, versus tapes or shields? Is it best to provide both in most scenarios?
Tapes and barriers do a great job of controlling spacing, of course, in the cable, and they control the coupling strength, as it were, between pairs within the cable. What's different about pairs and tapes and crosswebs compared to EMC or ANEX is that you have different wavelengths within the cable. So I would say you put the crossweb, the tape, whatever you need to control the pair-to-pair coupling. I would certainly expect, and our data tends to show, that is not an important factor in cable-to-cable disturbance. That's much more related to the energy radiating outside the cable, which is not really affected by the shape or size of spacers or physical structures within the cable.
Okay. Next, you mentioned optimum gap separation for the discontinuous shield cable. Can you elaborate on what the optimum gap is in your findings?
Not specific. I suspect there's several different gaps that can work. I will say this, which is important to say, is that all the cables that were tested and then all the data that is here are from cables manufactured by Hitachi. So these are all Hitachi cables that were tested. But we did explore a range of different gaps, and I don't want to get into the details of that yet, but the gap design does influence the overall performance of the cable.
Okay, thank you. Next, what is your thought on why the design D performed worse than the design U in the EMC testing?
It has to do with, again, the reason for the differences are captured in the way that the energy that radiates from the pair interacts with the barrier layer. And that's really the critical issue. And so depending on the design of the barrier layer, you will see different interactions with that barrier layer. And so, again, what we see in design D is that interaction essentially is allowed to, I'm not saying allowed, that interaction just has various frequency-dependent responses that tend to result in the curve that we're seeing.
Okay. Next, what about 2.5 and 5 gigabits per second protocols? How is the sensitivity compared to 10 gig?
The sensitivity of 2.5 and 5 is more similar to 10 gig than different because at 2.5 and 5, the transmission protocol goes to 16 level rather than the say 5 level, I think, at a gigabit. So the transmission protocol is very, very similar to 10 gigabit. What is different is the frequencies are lower, so you have a little bit less insertion loss and those kind of things. But no doubt about it, the 2.5 and 5 gigabit stresses the cables much harder than gigabit because of that structure. And so the standards do have things like even crosstalk mitigation built into the standards and mitigation techniques, et cetera. So there is more care and feeding, as it were, of particularly existing plant cable to reliably support 2.5 and 5. It is doable, it's done all the time, but it does require a bit more care and attention to detail.
Okay, thank you. I'm seeing no more questions posted. I wanted to thank you, Ken, for presenting this very interesting and important topic today. Please note the contact points being shown should you wish to contact Ken after today's event. Each of these IWCS webinar series presentation events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The IWCS webinar series will conduct presentation events on a monthly basis. Webinar events will take place on the third Friday of each month at 10:30 a.m. Eastern USA time. Our next scheduled webinar event will be on Friday, August 17th at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event a few weeks prior. Please feel free to share our announcements with your colleagues so that they can join in and register as well. For over 66 years, the IWCS International Cable and Connectivity Symposium has been the recognized leader showcasing new technologies in cable and connectivity products, processes, and applications. Our next annual international conference will take place on Sunday, October 14th through Wednesday, October 17th, 2018 at the Rhode Island Convention Center in Providence, Rhode Island, USA. In addition, the third annual UL and IWCS China Cable and Connectivity Symposium will take place on Monday, March 25th through Wednesday, March 27th, 2019 at the Shanghai International Convention Center in Pudong, China. Please visit our website at IWCS.org for more event details. In just a moment, you will see a brief survey so that you can provide us your feedback and comments on today's event so that we can further improve this webinar series for you. Thank you for participating, and this concludes today's event.